right. I wanted to kind of start tying some of these concepts to instrumentation. So I want to go through a couple really common instrumentation circuits, and not so much to train you to be an electrical engineer, so much as so that you can at least understand what's happening in certain circuits and how it relates to taking measurements. So one of the real common ones is called a current limiter. And for those of you who have been playing with your little kits, particularly those of you who have burned out an LED already, you've learned this. Basically, a current limiter just it's normally just a resistor, but basically the resistor drops the current in a series loop, so that the current throughout the entire loop is just lower. And so I'll go through a quick example of that. Well, actually, I'll go back to the schematic real quick. You see you've got your it says voltage input. You can imagine that being your battery. And you can imagine the VF here being like your little LED. So suppose and I'll draw this in the next one. So let's see if I can do this. I think I right click, pointer options. I'm gonna make this. There we are. Okay. So suppose you've got battery and our LED. Let's say this is 9 volts. And how much your voltage drops across your LED, and I'll put the arrow on here to indicate that it's an LED. So arrows through a component mean it's adjustable. Arrows like coming from a component mean it's emitting something. So in our case, it's an LED, so it's light. And I'll call this up here R. What you guys may have already tried, and have probably asked me for another LED if you have, is this mess right here. I've got a 9-volt battery and I dump it right across my LED. Well, if we remember our chart, there we have I and V. For an LED, remember we go to some knee voltage before we have anything happen. Then something like this. And remember there's this nice little X out here where basically we've exceeded some current and the LED burns up. The idea is if we have just a little tiny change in voltage, we can have a huge change in current. So basically what we end up with is if our knee voltage is, say, 1.7 volts, and yours will vary, I forget which color LEDs I've given you and what the specs on them are. This could be 2.2. It's going to be something like that, though, somewhere between about 1.5 and 2.5 volts. But if all of a sudden I apply 9 volts to it, I'm way out here on the curve, somewhere way up here. And you can see that that's way past our little X here, so our LED dies. Well, we don't want that. So what we do is we add this resistor here. The purpose of this resistor is to drop the current in the whole loop. Because in this case, if we think about this whole loop, we know that negative 9 volts plus I times R, and say we want our voltage across our LED to be just about the knee voltage. We know that our voltage, if we add up all the pieces of this loop, we know that that has to equal 0. So our first voltage here is 9 volts, and since it's the source, I gave it a negative. We know that our voltage across this resistor is I times R, and we know that we want our voltage across our LED to be 1.7 volts. And so a real common thing is, well, how do I find the value of the current limiting resistor? So basically what I can do is, I don't know R. And maybe I know I, we'll say, is 20 milliamps. I don't want to exceed 20 milliamps. Well, I can plug that in. 0, 2. That's 20 milliamps. And on the spot, I'm really bad. I'm okay at doing math, but on the spot, sometimes I'm bad at it. Let's see. Some of you have probably already figured this out if you're even paying attention, but I end up and so the minimum value of my resistor to limit the current there would be 365 ohms. And if you look at your kit, you'll notice that I don't think I have a single resistor that's less than 365 ohms for you. I don't remember what the lowest one is in there. It may be 470. But I chose my resistor values so that we could do this. So that's a current limiter, and it'll just depend how you've got your circuit set up. But the general idea is you want to be able to limit I by choosing an appropriate R. Okay, so that's how to limit the current through a device. Sometimes it's really hard to measure the current. So in your little circuits, not a big deal. Got a 9-volt battery. Plenty of kids used to lick the terminals, and it just doesn't have the capacity to generate a real high current, at least enough to really injure you. So, but that's not true in industry. In industry, we use a lot more than 9 volts. We use a lot bigger batteries and a lot bigger power supplies and such. So, if you think about how you had to measure current, where you had to break open the circuit and put your meter in place and hope for the best, open this so that your meter is part of the loop, that can be a little bit dangerous and a little bit, in general, you don't like opening up connections that are going to have high current through them, because just the littlest bit of dust or anything like that is adding resistance to your circuit. And so maybe you don't tighten it back down all the way or something like that. It's a real nuisance to measure current on high current applications. So instead, we take advantage of Ohm's law and we use a shunt resistor. And a shunt resistor is just this little copper bar here. And I'm pointing my screen like you can see my finger, but this little copper bar right here is your shunt resistor. And the idea is, this would go to the rest of our circuit, and then we would measure voltage here. Remember, we measure voltage in parallel. Well, we know this resistance is going to be some really small value, and we know the voltage, and we can measure the voltage, so from there we can find the current. So for example, suppose I've got some circuit like this, and I've got my shunt resistor. I don't know what that load is. I don't know what this source voltage is. Doesn't really matter. But got my voltmeter here. I want to know the current running through this loop. And I know that this resistor is 1/1000th of an ohm. We got some copper bar there. Sometimes you'll see that. It'll be a copper bar or a copper piece of pipe or whatever. We can say that our measured voltage, so we know that because we're measuring it with this meter here, and we know our resistance, because that's why it's a shunt resistor, is we know that resistance. So based on that, we can find our I. So this is a really good way to measure things. When I was a graduate student, we had a piece of equipment over in Jones Hall that was running 1,000 amps, and we actually had to run in the middle of the night, because if we tried to run during the day, there was enough people using power that we couldn't actually power the device. So we would come in 2 in the morning, something like that, to run the equipment. But the idea is that to measure current that high, we didn't go and break the circuit. And because like I say, suppose you accidentally got 1 ohm's worth of dust in there, that could be that would lower your total current. So the way we did it was we had the shunt resistor in there, we knew its resistance value, and then we measured the voltage across it, and so we knew how much current we were running. There's also kind of another way to do it, but for metering, this is a lot easier. We can measure voltage and it works out. There is a clamp type, so if this is your wire, and let me try, if I go over here, suppose that's your wire, there's a clamp that clamps over it, and basically measures the magnetic field, and you can find the current that way. And that's great for spot checking things. In fact, it's really good for things like, is there current flowing through here? But for, a piece of permanent instrumentation, it doesn't work out really well. It's really good for checking to see if there's current flowing, but not so great if you need to just be monitoring current for days and hours, or hours and days and weeks and months. It's better to just use a shunt resistor. Okay. One that's maybe a little less, or one that's a little more related to instrumentation is this, the idea here of a Wheatstone Bridge. And the way the Wheatstone Bridge works is, as it turns out, it's actually a little bit hard to measure resistance. And so, but it's really easy to detect even really small voltages. So what we do is we build a little resistor network. And you could work through the circuit dynamics, or the circuit, the network analysis, and figure out this. But if we know R1, we know R3, we know R2, then Rx, it isn't written this way, but pretend it's adjustable. As we change Rx, the voltage between D and B will change. And it may just change a little bit. It'll be really sensitive to any change in Rx. But what we end up doing is we look at this and we say, Rx may be attached to a strain gauge, maybe attached to a pressure sensor that uses a strain gauge, it may be attached to a thing called an RTD, which measures temperature. And so what we end up doing is we say, we start building this little chart where we say, I'm just going to draw it somewhere on here, Rx, pretend we got it attached to a temperature sensor. And actually Rx is going to change, but what we're going to measure is actually Vg. So maybe Vg, we detect 1 millivolt, and that's at 20 degrees in common units. Maybe 2 is 20.5 degrees C, and so on. And so basically what we end up doing is building this little calibration table so that we can look at this voltage. And the nice thing with stuff like an RTD is it's linear, so we can basically take whatever voltage we get here and convert it to a temperature that makes more sense. And so in software there's ways to do this. Idea being you would be measuring this voltage and corresponding it to a temperature. And so this little calibration you'd have to make, but then once it's there, it'll be pretty consistent. So that's the idea with that. Same thing goes for strain, same thing goes for pressure. And so Wheatstone Bridge is going to be really common in instrumentation. Another one that maybe you haven't seen before, in fact I'm 90% sure you haven't seen before, is what's known as a full-wave rectifier. And the way that works is, let's get a different pointer here. How do I do it? Pointer options, there it is. Okay, so this voltage source over here is AC. So alternating current. This is our peak voltage. Oops. And maybe this is, sorry, going the wrong way. Maybe this is 0. This is our positive peak, and this is our negative peak. And so this is switching at some frequency in the United States, 60 times a second, whatever it is. Now, plenty of devices, we want to have a direct current voltage, stuff like your cell phone charger, your laptop. We want something like 12 volts DC. But we're fed 120 volts AC. So that's what we've got over here. So we build this little network. And there's more to it than this, but I'll show you on the next slide. But let's say our positive, we're this part of the wave. So our current flows, comes to here. Well, these diodes only allow current to flow in one direction. So current can't flow back towards D4. It has to go through D1. So there we go. We've got our positive voltage here. How we get from 120 to 12, we'll talk about that in the next slide, but don't worry about that right now. What's really important is we've gone on our positive stroke here. We've got a positive output. Now we switch gears, and let's look at what happens on the negative stroke. So now we have current flowing this way. These two right here aren't connected, so we just kind of go through. And we get to here. Well, current can't flow back towards D2 because it's a diode and won't let it travel that direction. But it can flow this way. So we end up, once again, with positive voltage here. So what we end up with is this kind of pulse train, which if you squint your eyes kind of looks like a DC signal, like we'd like it to be like that, but we're getting closer, right? So when we start putting all this stuff together, this is an example of your phone charger. And like I say, we got our 120 volts here. We covered this piece. This is your full-wave rectifier. Maybe this is your cell phone plugged in over here. Maybe cell phone. This part here, this is a transformer. That's how we step up and down the voltage, and in a couple weeks I'll talk a lot more about transformers. But just know that that's how we go from 120 volts to say 12 volts or whatever we want. We can step up or step down the voltage. And if we step up the voltage, we have to step down the current. If we step down the voltage, we have to step up the current. We're not making or getting rid of energy, so that's why we have to do it that way. But just know that this is a transformer. And this is 60 hertz, and this out here maybe is 12 volts DC. Okay, now this piece in here, if you remember from our last slide, we had this pulse train coming in, right? And it's close to DC, but not quite perfect. So what we can do, switch options here again, in color red. We put this capacitor in here, and this is sometimes called a smoothing capacitor. And so basically at the peak here, we start charging the capacitor. We start charging it, somewhere down here. And when we get to the peak, this capacitor is now charged. Now our voltage starts to swing back down, and so we have this drop in our voltage. But now we can start discharging this capacitor. Then we get our upswing again. And we discharge this capacitor, and we discharge. We're basically charging on this part of each of these, and then discharging on this part of the wave. Anyway, the bottom line is we end up with this wave that instead of having these big, this pulse train, we end up with something that looks more like, and that little voltage is called the ripple voltage, and we want it to be as little as we can, but still practical. We could put a really big capacitor in your cell phone charger and have almost no ripple voltage. There'll always be some, but it would make a really tiny ripple voltage, except then you'd have to carry around this big capacitor. So it's always a compromise as to how much ripple voltage you can allow and how small you can make, and compact you can make your charger. So anyway, this is just kind of putting all these systems together. We'll talk about transformers later, and I just wanted to throw that out there. So hope you enjoyed.